Streaming. Hey, that does that. Okay. Does it look like it's streaming, Nancy?
Yeah.
Okay. All right. Welcome, everybody. Today we are mostly going to be working on proofs and getting more comfortable with doing them. And we'll do some induction examples as well. So for the very first one, I've got kind of the outline of the proof here. We're trying to prove the product of an odd integer and an even integer is always even. So I wanted to use this one as a warm-up because it's a lot more similar to the examples we've already done a couple of in lecture. So I want everyone to work on this for a few minutes and then someone volunteer for each number in the chat, and whoever volunteers first will just work through it as a class. Okay, so I'm gonna set aside, let's say 5 minutes. Is that long enough? I think, yeah, let's do 5 minutes and just work on this one for a minute. And go ahead. Okay, just about a minute more. All right, finish up what you're doing right now. And then is there anyone who wants to volunteer to do number 1? And I want to have someone different answer every single question. So who wants to volunteer for the first step?
I can.
Okay.
Okay, so the first variable can be m, and that'll be equal to 2p plus 1, where p is an integer.
And then
And
so why 2p plus 1?
because that's the definition of odd.
Okay, so for the very first step, we're just going to include which variables are odd and which are even. So that, because we can't apply those properties until we've declared that. And that was something that there were a few issues with on the quiz. So I just wanted to make sure that you get both of those in there. So sorry, I interrupted you. Keep going with the n.
Okay, so then n is even.
Okay. And then going based off of what he said, is there anyone who wants to volunteer for the second part? Where we're going to apply those properties of odd and even?
I can.
Awesome, thank you.
Okay, so n is going to equal 2k, where k is an integer based off the definition for even.
Okay. By definition of even.
And then
Okay.
m will equal 2p plus 1 by definition of odd.
Awesome, thank you, Misty. All right, and now we use substitution. We're given that the product of an odd integer and an even integer, so that tells us that we want to multiply m and n. So does anyone want to volunteer for that?
I can do it. Would that
Okay.
just be the 2k times 2p plus 1?
Yes, awesome. All right, and then when you multiply that out, what did you get?
I got, so it was 4pk plus 2k.
Awesome. All right, now moving on to step 4. Do we have a volunteer for factoring?
Just take a 2 out of it.
Let's see. It looks like actually, did somebody just raise their hand? Or no, it went away. Never mind. All right, if nobody new is volunteering, then go on. Is it Suban? Am I
Yeah.
saying that correct? Okay, go ahead and do step 4 for us.
You can just take a 2 out of the equation.
Okay, so m times n equals 2 times what is going to go in the parentheses?
2pk plus k.
2pk plus k. All right, step 5.
You just like apply closure under multiplication and addition and assign like 2pk plus k to like another variable like r or something. And
Okay,
that would
so
be an integer.
2pk plus k equals r by closure under addition and multiplication. And that means we can say that m times n equals 2r, where r is in the set of integers. All right, and then this is a step that is really easy to forget, but you have always got to close out the proof and make sure that you explain why what you just did proves the proposition. So is there someone who wants to write out a good conclusion?
Under the definition of even, m times n odd.
Under definition of even, m times n is even. So the proposition is true. And then you can put QED, or I always just do the box, but all right. So this is everything that would constitute a formal proof. So when you're doing it in your homework, just make sure that you're taking each of these steps and explain, include by definition of even and odd, include by closure, so that there is reasoning behind your work. All right, let's move on to our next one, which is going to be a problem on induction. And we'll do this one similarly, but I know we haven't done as nearly as many examples on this one. So I'll still let you work on it for a few minutes on your own, and then we'll work through it together. Okay, so let's give this one another 5 minutes. Okay, go ahead. Okay, that's 5 minutes. So let's start with the problem statement, which is that we want to show, we want to explain what P of n equals. Do we have any volunteers? And you can also put your answer in the chat if you're more comfortable with that.
Is it while n is greater than or equal to 1, it's n cubed minus n times by 3?
N is greater than or equal to 1. N cubed minus n, you said was equal to?
Isn't it like when it's divisible by 3, don't you write it as like times 3?
Oh, so yeah, there's a few different ways to write divisibility. So you could always do like 3 divides n cubed minus n. That would work. In this case, I think I would set it to be equal to 3k, where k is in the set of integers, because that works well with the math that we're going to have to do. But yeah, because it's a problem statement, you can write it any number of ways and it will be correct. And then let's see. It looks like there is a question in the chat. Yes, you can. You could also do n cubed minus n mod 3 equals 0. That would work as well for the problem statement. Okay, next is the base case. So because we are given that n is greater than or equal to 1, that kind of tells us that the base case is going to be P of 1, but that isn't always the case. If n starts at like 2, then the base case will be 2. So P of 1, I'll just do this one because it's a little bit more simple, is plugging 1 cubed minus 1, we know is just 0, and that is divisible by 3 because 3 times 0 is 0. So that proves the base case for us. So the inductive hypothesis is where it starts to get a little bit more tricky, especially because you're trying to choose if you're going to if you're using the inductive hypothesis to show n minus 1 or to show n. So for those of you that were able to finish the proof, did you notice that one worked better than the other? Okay, so for this problem, I would assume, so for the inductive hypothesis, we assume that the predicate is true for all numbers up to a certain point. And in this case, I would assume Pn is true. For all, let's see. Oh wait, no, not for all. Pn is true, so we assume that n cubed minus n equals, let's use a different variable, 3j, where j is in the set of integers. And we're going to assume that's true and then try and use that fact to show that Pn plus 1 is true. And that is one way to use induction. You could also assume that Pn minus 1 is true and use that to prove P of n. They're both doing the same thing, but sometimes the math works out better the other way.
Didn't you not do Pn minus 1 because n can only be greater than 1?
No, that's not exactly why, because, see, I'm trying to think of a way to explain this. The base case is already showing Oh, okay. You can always use Pn minus 1. It's just a matter of what kind of algebra you have to do, because the base case is there to show that, yes, it works for 1. So I guess this is really saying n is greater than 1 for in our case, sorry, let me get that out of the way. For n is greater than 1. But if you were doing Pn minus 1, you would want to clarify that it's for n, oops, for n is greater than 2, I think, or yeah, or n is greater than, I think, greater than 2. But just clarifying that you've already set up the base case. So I guess it'd be n greater than or equal to 2. That'd be accurate because we've already shown 1. Now we want to show all the rest of the numbers. But in this case, n is greater than 1 works fine. So now we're moving on to the inductive step, and we're trying to find a way to use our inductive hypothesis to prove Pn plus 1. So the first thing we want to do is plug in the n plus 1 to our original predicate, which is going to be n plus 1 cubed minus n plus 1. Okay. Any volunteers for multiplying out this polynomial?
It makes n cubed plus n squared plus 2n squared plus 2n plus n.
Oh, 3n squared plus, let's see, oh wait. Sorry, plus n, you said n squared plus 2n squared?
Yeah.
Okay.
Plus 2n plus n plus 1 and then minus n minus 1.
Awesome. All right, and then we can kind of move things around to combine like terms. And we know that we're trying to get towards this inductive hypothesis, which means that we probably want these two terms to be next to each other so that we can use substitution. So we're going to rewrite this as n cubed minus n, and then we can combine all these other like terms and put 3n squared plus 3n, and then those two ones just cancel out. So now we clarify, we're going to say by the inductive hypothesis, and we're going to use substitution here. So does anyone want to volunteer for what they put for their substitution? Okay, so we've got this term right here that matches our inductive hypothesis. So we know that this is equivalent to 3j plus 3n squared plus 3n. So now we can see that there's factoring we can do here. So we can pull the 3 out, and that gives us j plus n squared plus 3n. And we can recognize we showed that j is an integer.
It's supposed to be n, right? It's just
And
n.
You left a 3 inside the
Yeah.
parentheses.
oh, thank you. Yes, you're correct. Sorry about that. Okay, so we can use closure here, and that will give us the 3k where k is in the set of integers. And that's what we were looking to prove, which is that n plus 1 is still going to be divisible by 3. So now we need to do a conclusion, which is, let's see, Pn, let's see, ooh, that was supposed to be the, oh my goodness, why will this not click on the eraser? Okay, apparently I don't have an eraser anymore, so we're just gonna scribble it out. Pn plus 1 is divisible by 3 by definition of divisibility. So by induction, the proposition is true. All right. Okay, give me just 1 second. It looks like my screen just got frozen. So I'm going to stop screen sharing for 1 sec and just restart this app and see if we can get it to work again. Okay, it's working again. I have an eraser. Okay, does everyone understand each of those steps? Do we have any questions on induction? All right. So let's move on. We're going to do a number proof. Prove that if n is not divisible by 3, then n squared plus 2 is divisible by 3. So we kind of did a proof similar to this in our discussion last week, because we've got another one of these, n is not divisible by 3. And that kind of gives us a hint that it's going to be a proof by cases, because there are 2 different situations that n is not divisible by 3. And I accidentally scrolled a little far, so I gave it away a little bit, but does anyone want to volunteer to say what those cases are?
It would be when the remainder is 1 or when the remainder is 2.
Yes, awesome. So we've got those 2 cases right here. Let's see. Okay, so let's, just so that we can get through them a little bit faster, try and just choose one, and hopefully we end up kind of even in which case that we do. And that way we can have like half of you can throw out some answers for the first case and half of you throw out for the second case. So just go ahead and choose one of these, and I'm going to give you 2 minutes to 3 minutes actually, just to go through that. Okay, go ahead. All right, so let's work on the first case. Who wants to volunteer to get started on it?
Since n is equal to 3k plus 1, where k is an integer, you can just plug in 3k plus 1 into the n squared plus 2 equation.
Which gives us 3k plus 1 squared plus 2, and what does that simplify out to?
9k squared plus 6k plus 1 plus 2.
All right, and then we can combine like terms to get 9k squared plus 6k plus 3. And then what's the next thing that we need to do?
Factor out of 3.
Okay, so we'll pull out the 3, which gives us 3k squared plus 2k plus 1. All right, and then we can use closure and get 3c, where c is in the set of real integers, and c is equal to 3k squared plus 2k plus 1 by closure. And usually I would specify closure under multiplication and addition, just to be specific. But there's not a lot of room on here, so we're just gonna say by closure. So n squared plus 2 equals 3c. So let's see. So n squared plus 2 is divisible by 3 by definition of divisibility. Okay, and then again, the second case is always going to be a little bit easier than the first one because they're usually pretty similar. So it'll be similar steps. We'll again have n squared plus 2 equals 3k plus 2 this time squared plus 2. And then what does that multiply out to?
I have 9k squared plus 12k plus 4 plus 2.
All right, awesome. And again, we can factor out, or not factor, skipped a step, combine like terms. Okay, and now we can factor out of 3, which leaves us with 3k squared plus 4k plus 2. And then we can apply closure again. And remember, we can use all these same variables because the cases are independent. By closure. And then again, we would put n squared plus 2 is etc. Usually you should write that whole thing out, but we're just going to shortcut it right now. I'll at least write divisible by 3. And then we still need to have our conclusion, especially in proof by cases. It's good to just say, since both of the above cases are true, the proposition is true. All right. Any questions on that process? All right, it looks like we've got about 9 or 10 minutes left. So let's see. I think I'm going to skip this problem on counterexamples because I think after the first quiz, we probably have a good grip on those a little bit better. So I'm going to try and get this number proof done before we finish because it's a little bit tricky. I think it's a good one to practice with. So we are trying to prove that 7 is the only prime number that precedes a perfect cube. And our hint is, how does the polynomial x cubed minus 1 factor? So it's kind of hard to get started on this one because usually we're given an if-then statement and we can take the if portion and start working on properties, but this one is a little bit more, it's not as obvious where the starting point is. So what I like to do is just kind of like go over the things that I know, the things that I've been given in the statement. So in this case, we know that a perfect cube is represented by x cubed. And we know that the number preceding it is going to be x cubed minus 1. That gives us a good starting point to start working with variables and figure out how all of this works. And we also were given the hint, how does the polynomial x cubed minus 1 factor? So does anyone know how x cubed minus 1 factors? It's kind of tricky.
Is it x plus 1 times by x squared minus 1?
Not quite. So I'll do the first term. It's x minus 1. So we're close on that one. And then the second one is going to be a little bit more tricky. Does anyone want to try for the second term? Okay, so the second term is actually x squared plus x plus 1. And if you multiply out, you'll see that the two x's end up canceling each other out. And that's how we end up with the x cubed minus 1. So we know that the factors of x cubed minus 1 are x minus 1 and x squared plus x plus 1. And because we're looking at prime numbers, we are really focused on seeing if either of these two factors turn out to be greater than 1, because that indicates that there is a factor other than 1, which means that it is not a prime number. So the first thing that we know about prime numbers is that they have to be greater than 1. So we know that this, let's see. Let's assume that x cubed minus 1 is greater than 1. So basically we're trying to get x cubed minus 1 to be a prime number. We're just assuming that that is the case, and we're trying to prove that it is impossible for any number other than 7. And let's see. This tells us that, so if you do the algebra on this, this turns into x cubed is greater than 2. So this kind of tells us that x also has to be greater than 1, because 1 cubed is just going to be 1, and 2 cubed is going to be 8. And 2 cubed is the case, 2 cubed minus 1 is 7. So that is, remember that we're focusing on 7 is the only prime number. So we've ruled out 1 as being the perfect cube, and we've ruled out 2 as being the only one that, as being the only number that does have a prime number before it. So we know that those two are the case. So now we're looking at numbers that are greater than 3 and greater. And we're trying to prove that none of those numbers are going to create a prime number. So let's see. So we're trying to show that for all x is greater than 2, x minus 1 has to be greater than 1, or x squared plus x plus 1 has to be greater than 1, because these are both factors of x cubed minus 1. All right, is everyone still with me? I know it's kind of confusing. All right, I'm going to go on. Let's see. So in both of these cases, if you plug in any number greater than 2, we are going to end up with something that is greater than 1. So in this case, if we plug in 3, we get 3 minus 1 equals 2. So that's greater than 1. And if we plug in 3 here, we get 3 squared plus 3 plus 1, which is, we don't even have to solve that to know that that is also greater than 1. So we've shown that 7 has to be the only prime number that precedes a perfect cube, because in all of these other cases, you have factors that are going to be a number other than 1. So now we can say that x cubed minus 1 is not prime except when x equals 2. Okay. Does everyone follow that and the logic behind it all? It's totally okay if you got lost a little in there. We can go back to some of these other steps because we've got a couple more minutes.
So if it's like, if x was any other number, then it would not be considered prime.
Yeah, because we've gone through the cases. We know that it can't be negative because cubing a negative number and subtracting 1 is going to be negative. So those are never going to be directly before a perfect cube. So we've eliminated all of the negative integers. We said that we found out that x had to be greater than 1 over here. And then we found that 2 works, but anything greater than 2 is going to end up being resulting in factors that are greater than 1.
I think there might be a more intuitive way to do this. So like
Okay.
for x cubed minus 1 to be a prime number, which means either x minus 1 is 1 or x squared plus x plus 1 is 1. So
or x squared plus x plus 1 equals 1.
yeah, and for the first case, x would be 0.
X equals, oh,
2, sorry.
oh, okay. X equals 2.
Yeah, and then for that, x cubed minus 1 would be, you would get 7. And
So
for the, yeah.
Here. I'm trying to like show how we're plugging that
Yeah.
into, which gives us 2 cubed minus 1 equals 7.
Yeah, and for the second case, I think you would get x squared plus x equals 0, and then your x gonna be 0. And if you plug in that into x cubed minus 1, you would get -1, which is not a prime number.
Okay.
And I think this will give you only 7 is the only prime number. that precedes perfect cube.
Okay.
Yeah, because for this one, I think we're just using the definition of the prime number, which means one of the factor has to be 1. So either x minus 1 is going to be 1, or x squared plus x plus 1 going to be 1.
Okay, did that help out anybody who is still a little bit lost? So this is just kind of another possible solution. So I'll just put so either one of those works, but there is, like Nancy said, this one is a little bit more intuitive. It just kind of depends on what you're able to use when you're in the moment and like trying to figure out how to manipulate the numbers. So this one is solution one is a little bit more of a workaround, but that's kind of like where my brain automatically went to. And that just kind of shows that there's a few different ways to do each problem, as long as you're using properties about numbers to prove the statement. All right, and then it looks like we are a little bit over, so I will go ahead and let you all go. Sorry about that. And if anybody has any other questions, feel free to stay after and ask us.
Thank you.
And then sorry, what?
I'm just want to ask, like, who's going to be the lecturer for next session?
I'm pretty sure it's, actually, I don't know. But it looks like James just got here. James, are you the lecturer for the next session? I feel like I ask you this literally every week.
I don't think we can hear you.
Oh, and I'm gonna stop sharing. Oh, whoops, and stop